Hello, in the last video we introduced the beam deflection, and it's all started with this formula of m equal to ei v prime, right? And then we go ahead and integrate twice, and we use boundary condition to find a constant. And the example we did, I believe, is this cantilever beam with concentrated load at the end. It's this one. And what we have come up for the deflection formula after you integrate is V equal to P, I believe is P x cubed over 6 minus x squared L over 2, and then divided by EI. Okay, that's the one you calculated. Now let's take a look. This is a deflection, and today the main topic is I want to introduce Appendix C in your textbook. And for example, this column, elastic curve, that's basically telling us V as a function of x, deflection as a function of x. So is this formula same as this one? So if we were trying to make this as close as this one, we're going to take 6 out, take x squared, and take 6 out. Okay, so you still have EI. And since it's x squared 6, and then we'll just have x left in the parenthesis, and then we'll have 3, then L. We'll have something like that. And this equation is essentially the same as this one. The only difference is I'm taking negative out, then in the parenthesis I will flip the place will be 3L minus x. So you got the expression that's same thing listed in the table. That's deflection. And now let's look at another column. Over here, the deflection, this one is list the maximum. I know where maximum occur, right? For this particular problem, the maximum occur when x is equal to the end of the beam, when x equal to L. So when you put that when you put x equal to L, this V become V max, and we can put it in there, 6EI, and x is L, PL squared, and L minus 3L. Then let's take a look. We'll have 6EI, and here we'll have negative 2PL cubed. And if we cancel out, that would be EI, 3EI, and then negative PL cubed. So that happened to be the same value here. Okay, so one thing I want to discuss is, for some beam, might not be that obvious where the maximum deflection occur. So in that situation, how do we figure out? I want you to use the calculus knowledge. In order to find a maximum, we always realize the slope is equal to 0. So if you can find a V prime, which is the slope of the deflection, equal to 0, then you are going to get V maximum. So knowing that principle, remember when you integrate the first time of this, you will get V prime expression, right? And you can list that equal to 0, V prime equal to 0, then you will find x equal to some certain value. Then you know where exactly on the beam where you see the maximum maximum deflection. And then knowing that maximum deflection location, you put x in here, then you can find the V max. So that's one way to get around when the maximum deflection is not that obvious, but you can still do it. Okay, then now let's look at this first column here. They have slope. The slope basically is your V prime. We're talking about last time V prime is also written as theta x in some place, right? And by here, since this slope is also a function, because v prime is a function here, and they want you to know what is the maximum slope. For this cantilever beam with concentrated load at the end, obviously the maximum slope is also happening at the very end when x equal to L. So if you still, let's go back to what we had before. So this is deflection, and this is where the slope is. That's where v prime. So if I'm going to copy that one there, oops, yeah. So what I'm going to do is I'm going to actually copy that one. Yeah, looks like I can. And I'm going to go over here. Oops, I guess not right. Okay, so go back to the notes you have written for the previous problem. You will have the EI prime. I'm going to write it down now. So EI prime is going to be equal to EIV prime, sorry, is going to be equal to P x squared over 2 minus Lx, okay? So here you get expression for V prime, which is the slope of the deflection, and that gives us answer is P x squared over 2 minus Lx, then divided by EI. And when will this to be slope will be maximum? We already know it's for this situation is at x equal to L. So if you plug that in there, V prime will be equal to EI and P x equal to L, and so that will become L squared. And the answer for that one will become negative 2 PL squared EI. And hopefully that is exactly in the table. That's right, negative PL squared over 2EI. That is a maximum slope. And if you just don't want to find a maximum slope, you want to find a slope expression, and that will be, okay? So here you get maximum of slope. So imagine if you have done all this type of the beam, list over here, using starting with this governing equation and integrate, and considering the boundary condition, you will find all those properties here. The elastic curve, which means the shear, no, I keep on saying shear, sorry, deflection function, and also you will find where maximum deflection happens, and you also will find the maximum slope happens. So this is a very helpful table, since once you've done one, you don't need to do all of them unless you're really bored. And however, use this table to solve any deflection problem, right? So for example, they give you a simply supported beam like this one, and have a concentrated in the middle. They want you to find out where the maximum deflection is and what will be the value. Then you come to this one. Deflection, the maximum value, it's this one, right? And where will be maximum slope occurs? Very likely the maximum slope occurs, what you can see here, zeta max. That's going to be at the very left end and also on the very right end because it's symmetric. So that's going to be the maximum slope, because when the maximum deflection happens right in the middle, the slope here, you can see it's going to be equal to 0 right here. However, the deflection, the slope is a maximum at the very left and very right end. All right, so hopefully this will help you to solve any deflection problem, and I'll see you at the next video. Bye.